Okay, so today I'm talking about a couple things. We're back talking about rational functions. We're talking about limits. We're going to talk about reciprocal functions a little bit. It's going to be important to keep all those different vocabulary terms separated. But the first thing I want to talk about is this idea of limits to infinity. And the way you'll see this written, this is terminology that we've been over, but only a little bit. What's the limit of f of x as x goes to infinity? And so the limit of f of x as x goes to infinity means what is the function doing as, remember this is x and this is y, as x goes further and further to the right, what is y doing? And in this case, if this were the function, it's going up, so the limit would be infinity. And it's also possible to ask these questions about negative infinity. And so let's say maybe this function has a little asymptote here, and the asymptote is at -5. If the question asks the limit of f of x as x goes to negative infinity, it might be -5. Okay, so those are the types of things we're doing, and I'm going to do most of my work on Desmos now going forward. But just wanted to show you that's the type of thing that the question would ask that we're talking about. And so now we're going to be talking specifically about rational functions. Okay, so see, I'm going to go through f, g, and then h, and we want to use some intuition to decide what's it going to look like before I click this button. Once I click this button, you'll see the graph and you'll know the answer. But take a look at this. In the first function, I have a rational function. On the top, I have x to the fourth minus 3x squared plus 2x minus 5. On the bottom, I have x squared minus x plus 8. Now, when you're looking at these, what you want to look at is the term with the highest exponent in each the top and the bottom. Okay, so on the top, the degree of the polynomial is 4. On the bottom, the degree of the polynomial is 2. The reason we only care about that term is because it grows so much faster than the other terms in that expression that as x goes up and up and up, this term is going to drown out the other terms. These, when we're close to 0, when we're close to 10 even, this 3x squared and 2x and 5, they matter. This negative x, this plus 8, they matter. They affect the value of the expression. But when we get up to like 100 or 100 million, these terms are not going to matter at all. So we're talking about limits as x goes to infinity. We're only looking at these terms here. And so notice that the higher degree is in the is in the numerator. It's on top. When the higher degree is on top, the function is always either going to go to positive infinity or negative infinity. So if I show this, the limit of f of x as x goes to infinity is infinity because it's pointing up. The limit of f of x as x goes to negative infinity is also positive infinity because it's pointing up. So that's situation 1. Situation 1 is when the higher degree is on the top than on the bottom. Situation 2, guess what? We're going to flip situation 1. Now we put the higher degree on the bottom. What do you think is going to happen? If you're thinking that the bottom is going to grow faster than the top, you're thinking correctly. And what's the limit going to be? You might think, well, maybe it'll be negative infinity. However, that's not how a fraction works. If you think about what happens when you have the bottom growing, let's say I have 10 over 12, then I have 12 over 24, then I have, let's say 14 over 36, let's see, 48, then I have 16 over 96. What's happening to the values of these fractions? They're getting smaller and smaller and smaller, okay? And what are they approaching? If I go up another one, 18 divided by 192, they're going to 0, okay? So when you have the denominator of a fraction growing faster than the numerator, the value is approaching 0. So if I click this, what you're going to see is that there's a little bit of noise, and there's an asymptote in here somewhere, but I'm not too worried about the asymptote. What I see is that I'm not too worried about the vertical asymptote right now. I can figure out what it is. It's whatever makes this expression equal to 0, but that would take a little bit of time. What you should notice is that there is a horizontal asymptote at y equals 0. And the horizontal asymptote is something that the function approaches infinitely but never actually touches. But this is like the one situation where the function does go through it. It crosses that asymptote. So it's possible in some situations for a function to cross its horizontal asymptote if it's an infinite limit, if it's a limit as the function goes to infinity. But you can see on both sides of this function, both as x goes to infinity and as x goes to negative infinity, the function is getting infinitely close to 0, but it's never actually touching 0. And so then the first scenario is when the numerator is bigger than the denominator, and that's infinity or negative infinity. The next situation is the denominator is bigger than the numerator, and that's 0 or negative 0, but that's still 0. And the third situation is when the denominator and the numerator have the same degree, like in h of x. Okay, so in h of x, I have 7x squared minus 3x plus 5, and I have x squared minus x minus 4. And if I look at that, well, I'm zoomed out here. Now I got to zoom in. Well, it looks like there is an asymptote. It's not at 0, but clearly this function bottoms out. And if I wonder what the asymptote is, it's 7. Okay, and so the function never really gets to 7 on either side. It's going to approach infinitely 7. And if you want to know the algebraic way for solving this is if I say limit of f of x as x goes to infinity of that expression there, what I really have to do is just take out the two terms that are dominant, the dominant terms, 7x squared over x squared, and the x squareds cancel, and I get 7. Okay, and so you can do that. You can use those algebraic steps with limits if you have the denominator that's the same. Or you can just kind of look and know if I change this to 8, then this would change to 8. If I change this to 2, then you might think, what does this change to? Well, it changes to 8 divided by 2, which is 4. Okay, so that's how those work. And then the second thing that I want to talk to you about is reciprocal functions. And so what's a reciprocal? A reciprocal is a fraction. So if I have these numbers 1, 2, actually let's do some negative numbers. Negative 5, negative 1, 1, 5, 10, negative 10. And if I take the reciprocal, I have negative 1/10, I have negative 1/5, I have negative 1, I have 1, I have 1/5, and I have 1/10. What happens to a reciprocal as the number gets larger, the reciprocal gets smaller. So when y goes to infinity on the original function, the reciprocal is going to go to 0. And that's the same thing in the positive and the negative direction. And the other thing to recognize is that the signs don't change. The reciprocal of a positive number is still positive. The reciprocal of a negative number is still negative. So if I think of, oh, look at this. This is an easy function. B is equal to x minus 6. And I think, what's its reciprocal going to look like? Well, by the way, the thing that I didn't put on this number line was 0. The reason I didn't put it in there is because you can't divide by 0. But you should know when you try to divide 1 by 0 or any number by 0, it doesn't exist, and so the correct answer is undefined. But it's a lot like the number infinity. Okay, if you were to take $1 and to try to divide them up into piles of 0 cents, how many piles would you have? Well, you'd have infinitely many, because you could keep making pile after pile after pile after pile after pile after pile, and you could keep going forever and ever and ever and ever and ever and ever. So now we notice this point this function has where x is equal to 6 and y is equal to 0. Something is going to be going on in that function. So if that's the function itself. This is the reciprocal function. I made it orange, I made it dashed. And I'll just take a little screenshot of that, and we'll look at two of these and just notice some common features of both of them. And so the second one is going to be a parabola. You might say to yourself, where is this function going to have zeros? It should have zeros at -2 and at 3. And then you might ask yourself, what's the reciprocal going to look like? The reciprocal is going to have something interesting going on at these 2 points that are x-intercepts on the function. It also, this one is a little more interesting than the last function. It has a local minimum. And so you might ask yourself, what's going to happen at that value where the direction changes? Let's look. Interesting. And it's a little bit hard to tell from here, but I'll tell you this, that where this function has a minimum, the other function has a maximum. Okay, so this value right here lines up with some kind of a maximum value right there. And that's going to be true for these things too. But let me go back to dashed. And I just want to show that this is going to be true. This is the first example that we had. And we had the 0 here. And we had the 0 in the original function. In the reciprocal, we had an asymptote. Where the function went to infinity, the reciprocal went to 0. Where the function went to -infinity, the reciprocal went to 0, but instead of from the top, from the bottom, from the negative side. In the second example, we had 2 zeros on the original function, and we got from them 2 vertical asymptotes. And this looks a little bit sloppy, but it should be an asymptote that doesn't cross right there. We had where the function was negative, the reciprocal stayed negative. However, the local minimum became a local maximum. Okay, where the function went to infinity, the reciprocal function went to 0. Where the function went to infinity, the reciprocal function went to 0. So there is that relationship between these things, between a function and its reciprocal function, and you're going to explore a little bit more with it today. But I thought that overview might be helpful.